Hello, and thank you for coming to my talk at the Culture Meet Symposium. I'm going to talk today about some of our challenges for food system development for space exploration, and hopefully it'll help everyone here when they think about how can the systems that you're working on be used in space flight, and how will they impact those resources, and how can we get them to integrate within those resources and provide a solution. So when we think about developing food for spaceflight, we need to make sure that that food is safe and nutritious, not only providing all nutrients, but also providing nutrients in a variety of acceptable foods so that crew can find the foods that they want to eat within their mission. So acceptability we find is incredibly important to this, especially as missions become longer and further from Earth, that finding foods that you want to eat also becomes more important, and foods are central to crew gatherings, to holidays, and they're also central to crew cohesion. And that can be more so even than here on Earth, because food is one of the only things that is still familiar and comforting in the spaceflight environment. In addition to this, the food must promote human health and performance. So the crew needs to find foods that they want to eat that's going to give them their nutrition and maintain their weight and their health in order to support them to do very challenging tasks that demand high performance and high cognitive skills. And often in conflict with these first two challenges is that the food must fit within very tight resource constraints. So in the past, these are some of the challenges that NASA has had to meet when developing food systems. The food system is closed, which means that once it launches, you cannot introduce new foods. So that's why we have to provide all the nutrition and make sure that this food system is safe. We have to have a multi-year shelf stability, even for the International Space Station, because by the time we prepare the food and package the food and send it to launch and it launches, it often is over a year old by the time the crew actually gets to consume that food. This multi-year shelf stability has to occur with no cold storage. So most missions to date have had no cold storage. Missions in the future might still have no cold storage. It's a huge resource use. We've had no cooking to date. That's also a huge resource use, and cooking in microgravity would provide a lot of new challenges. We have to limit crumbs and free liquids because in microgravity they float, and that can be a challenge, especially if you have a hot liquid or if you have crumbs and they end up going into instrumentation. So we have to eliminate that. And so we cannot really transfer food in spaceflight either. We need to have a certain surface tension so that when the crew is eating the food, it stays within the package or on their utensil. And in addition to that, there's not a lot of food time for food preparation. It's basically heat or add water. And there's no washing or reuse of containers. So the food eats right out of their containers and they throw them away. And our packaging right now is all lightweight, flexible packaging to minimize this resource as well. Most water on the International Space Station is recycled, and future spacecraft for long duration missions will also have to recycle most of their water, and crew get about 2.5 liters per person per day for regular food and drinking purposes. So NASA's dealt with these challenges in the past by providing tubes and cubes on the Mercury missions. So the gelatin-coated cubes prevented crumbs and they could just stick them in their mouths, and the tubes they could just squeeze them into their mouths. But considering that food acceptability is important, this is not the most acceptable food system. The food systems did continue to get better. In Gemini, they added a water gun and they were able to rehydrate some foods, and they would just cut them open and squeeze them into their mouths. Still not the most acceptable system though. Apollo added canned foods and hot water for the first time, as well as utensils. And so the food system was getting more acceptable. But all of these food systems were under-consumed, and crew, even on these short missions, lost weight, which is a concern in microgravity as far as bone loss and muscle mass loss. And that gets worse as the missions get longer. Skylab was considered one of the most acceptable food systems because they did have some frozen foods. However, it took longer to heat up the frozen foods, and the crew actually was very busy with science experiments on these missions. They commented on having a food system that was easy to prepare and quick to prepare being very important, so the crew could eat together within very limited time frames, and that this food system often didn't allow them to eat together because it took too long to heat up and prepare. So the shuttle food system was the first food system to go to lightweight flexible packaging because the crews got larger and they had to have a way to store all the food going up and also to store all the trash. So the lightweight flexible packaging enabled easier use of the space that they did have. They had a convection food warmer on these missions and also hot and cold water. This food system also had about 130 different options, and this was the first food system that was also used on the International Space Station. But the crews found as the missions were longer, this didn't work as well, especially because on the shuttle, the food launched with the crew and they launched a preference menu. So crew would come to the lab, they would try the food, they'd work with the dietitian to set up a menu specific to that crew that met nutritional requirements and also crew preference. Well, on the International Space Station, the food was resupplied. So there were two issues here. One was that the 130 options that were available on shuttle didn't work as well for these 6-month missions. And there were resupply delays, which meant that the preference foods did not always coincide with the correct crew. So the average body mass loss was around 5%, and they did see some crew lose up to 10%, which is pretty substantial, as this does result in significant bone and muscle loss and cardiovascular deconditioning. So eating foods that someone else chooses is not necessarily the best option. So there were some changes to the ISS food system to date. One was that we moved away from preference containers to standard categories. So this was packed more pantry style, and there were 8 categories currently that feed a crew of 3 for about 7 to 9 days on a rotation. So there's a lot of variety in this, which works out great if all the crew members want something different, but there's not a lot of servings of each type of food. So you're still in a limited mass system. So you still can only launch a limited amount of things. So if you increase variety, you decrease the number of packages of each food in those containers. Now, the crew are supplemented on the International Space Station with some personal preference containers that are able to be pre-positioned for the crews that are going up there. So this is still more limited since they do not fly with the crew. So in those personal preference containers, they can pick some more of their favorites and make sure that they are able to get some of the foods that they really, really want on a more regular basis. They also get condiments and fresh foods periodically on resupply vehicles. One of the other things that we did was increase the variety in the standard menu, so from about 130 to 200 different items, and also there was a consideration that sodium was exacerbating some of the negative physiological changes in spaceflight. So there was a major effort to reduce the sodium in this food system. This is a pretty significant effort. This is a completely prepackaged shelf-stable food system. So in general, if you are using more commercial foods, there is a higher sodium content. Sodium does have a lot of flavor. And so we worked to reduce that. And there were more foods that were developed to meet the nutritional requirements of spaceflight at the Johnson Space Center. So in addition to this, on the International Space Station, there's limited food preparation equipment still. There's hot metered water, ambient water, food warmer, so it heats by conduction, and a small chiller that enables them to heat some beverages. And they did find within this time that with adequate food intake and resistive exercise using the advanced resistive exercise device, crew members could maintain their body mass and bone density. There were some crew that did this. It was not all crew, but it was positive as we move towards the future to find that if we are feeding the crew in a way that they can find choices they want to eat, and if they're eating enough, and if they're exercising, that they can maintain their body mass and bone density. So I mentioned before about the role of acceptability, and food variety is incredibly important to support intake and human health and performance. And we can see that just by the number of pictures crew take when they're really enjoying their food. So on the International Space Station and low Earth orbit, there is a lot more resupply, especially in recent years with the role of the commercial vehicles bringing up more supplies regularly. And so there are some late stow items like pizza kits that only have a few weeks shelf life. There's fresh produce that has a very short shelf life that we can send to the International Space Station. And crew really, really enjoy these special types of foods that they are able to get right now. They also get coffee and tea to preference, and occasionally a powered freezer will go up to the International Space Station and they'll get some ice cream. So this just shows the role and how important this is, and crew do often ask for more crew preference foods, more variety, more choice. They say variety and choice is one of the most important things to continuing to be interested in your food system when you're in a closed, limited food system. And yet we still do see crew under consume. And we have also learned a lot from the International Space Station about human physiology, which is very important as we move to long duration. So we do see increased stress and potential for anxiety and depression with that increased stress. We see changes in the way some bacteria express. We see alterations in the immune system and the microbiome, and we continue to see body mass loss and muscle loss, even with the food system improvements and the variety that's available on the International Space Station. Now, as we get further from Earth and the missions get longer, our resources might even get more restricted. And so we need to find ways of providing solutions to some of these human physiological changes that are not going to be as impacting on the resources. And we're going to be bringing food anyway on these missions. So looking at food as a countermeasure, diet as a countermeasure, we can look at food now on the ground and really start to try and develop it in a way that we're making sure that it's high quality, that crew want to eat it, and that it's interacting with our physiology in a way that's truly promoting health. We know that what we're eating is impacting our microbiome, creating metabolites that are impacting our immune system, our gut-brain axis, basically every physiological system. And so how we're feeding our bodies and the metabolites that are being produced and interacting with these systems becomes very important in order to provide diet as a countermeasure. And we can start to really understand that now and make sure we're providing the right food systems now, even as we are limited in resources and limited in the food that we can provide. And this is very, very important as we go on these long duration missions. Now, with that challenge comes the challenge that we have to fit within a smaller resource box. And this is very, very, very complicated, because when we think about the food system, a lot of the resources that go into food happen on the ground as far as agriculture and production. And we're just taking the product of that right now into spaceflight. Now that product has a high mass going up into spaceflight, but in order to fit within that box, any food system that we use has to fit within that box as far as the volatiles it's producing into the environment, its ability to interact with the water system, the power system, and the crew themselves. So this is a big challenge as we go forward to fit all of that nutrition, that acceptability, that safety into this box. And this gets more challenging as we look to Mars missions, which are up to 3 years, portions of microgravity and reduced gravity. And due to planetary physics, we probably won't have resupply, and food may even be pre-positioned ahead of the crew. Additionally, because it's such a huge resource use, there still might be no or limited cold storage. And in addition to this, because food may be pre-positioned, even before crew is chosen, we might not be able to provide them as much preference or really any preference. We'll still be sending a standard menu, and we have to figure out how to set that up in a way that we can support crews that are changing and different needs and wants within that in order to encourage crew to eat and maintain their health and performance. Now, there's actually no precedent for a food system like this. A food system like this, we think, would need about a 5-year shelf life, because by the time we ship it, launch it, pre-position it, and the crew's eating it at the end of the mission, it might be 5 years old. So if we look back to the age of sail, crew were actually coming in regularly to port every couple of months at the most, and yet they still had more cases of scurvy, and more sailors died of scurvy than all other causes combined. If we look at Antarctic missions, which were more like spaceflight missions, crew were off for up to 2 years in some cases They even had the capability to freeze foods and to hunt. And yet still in these situations, food was one of the biggest challenges. They lost a lot of missions due to not having enough food or to malnutrition. And if we look at the modern US military, they've done studies where they see that if they're feeding meals ready to eat, MREs for long periods of time, they see that their warfighters in the field are eating less, and it does eventually impact health and performance. And therefore, they try to limit the use of meals ready to eat to 21 days. Now in spaceflight, we don't have that option. We cannot provide another food system at this point. And so we also know that we have some constraints with our prepackaged food system that we're currently providing, such as we see nutrients degrade over time. We see quality degrade over time. We know that it's high mass and volume initially, although it does not take a lot of resources in spaceflight, and that there's not a lot of ability to customize besides adding condiments. If we look at the nutrients within that food system, so if we look specifically here at vitamin C, which is a very labile nutrient in our fruit products on the y-axis, and we look at the milligrams of vitamin C per serving on the x-axis, this is over 3 years. The blue bars initially after production, the red bars after a year, and the black bars after 3 years. We lose more than 50% of vitamin C, and this isn't even the 5-year shelf life. We often get asked, why not provide a supplement? Well, there's a few reasons. Nutrients degrade in supplements as well. In addition to that, you have compliance. Crew want to eat what they want to eat. And if you're on a very long mission and you need to eat a supplement, there's a couple things that will happen. Either you might not get 100% compliance, and additionally, you might have crew considering that, well, if they took the supplement, it's not as bad if they don't eat as much. And you cannot take a supplement for calories or for the thousands of other phytochemicals that are being provided by a whole complete food system. So it's very important both for crew to get their calories and to get all of the nutrition from food, that they're eating a whole food system, and that we're maintaining the quality of that food system and the nutrition in that food system so that they can get all of their food needs from a whole complete food system. So this goes back to variety and acceptability again. We know that food quality relates to health and performance. And we also see that food variety is limited in a closed system, and that our system does have decreased quality over shelf life. So we looked at our thermostabilized items and found that only about 7 of them would be expected to still be acceptable after 5 years. So this is at room temperature, and this is definitely a challenge, especially as food becomes more important with the length of the mission. So we need to find solutions for these things. So if we look at a food system for exploration, we don't eat one way on Earth. So we probably would not eat one way in spaceflight either. So prepackaged foods, they have a lot of benefits, and we still look at them as part of a solution, and just how can we improve upon our prepackaged food system. We can also look at bioregenerative foods, and how do we start adding in situ grown foods into that system in a way that they integrate with the resources that we have available. And then also, is there a way to provide automated nutrition in even a personalized way? So that would be a very future novel concept to be able to do that as we start to understand that more. So there is a case for continuing to use prepackaged food. One is that food safety is confirmed prior to launch, which is very, very important. If we start producing something in spaceflight, how do we confirm that safety in spaceflight? Right now, the resources that you need to confirm safety, run the safety tests, and also the waste produced from that generates a whole nother stream of consideration for the resources in spaceflight. And we don't have that capability right now in spaceflight. So all of that consideration would have to be added to any food system that was generated in spaceflight. Additionally, the prepackaged food system doesn't need a lot of infrastructure or crew time, which becomes very important if you're thinking about an exploration mission where they're going to be out on extravehicular surface activities continually. And like us, they want to be able to go home and enjoy a meal with very minimal time required and have the process be enjoyable to prepare that food. Additionally, prepackaged foods, they basically eliminate the risk of food scarcity. If the food is there and if the packaging is intact, then you have food, which if you're trying to grow food and you lose that and you're dependent on it and there's no other source, now you're in an issue where you might have starvation. And that's something we want to definitely eliminate that risk. So prepackaged foods have already demonstrated a lot of great qualities, and they've been able to support human health and performance on the International Space Station for 6 to 12 months. So we definitely see them as part of a solution. And we are looking at strategies to extend their shelf life. We're looking at different formulas that do better. And we're looking at new processes and new packaging that is compatible with that processing that might be able to extend the shelf life. And then also the environment. So what exactly will cold storage buy us? Can we get to a 5-year shelf life? Which foods need to be stored in a cold environment? Maybe some of them do okay without it. Maybe some of them do okay with just a slightly colder environment. So which foods do we have to store at different temperatures? Because that can have an impact on resources too. And so we are looking at, can we achieve that 5-year shelf life right now? And we do see some changes really quickly with some of our foods. So this is dried apricots, and this is just after 1 year of storage. And we can see color changes very quickly. So there's a quality change, but that color change also shows up with a nutritional change. So the apricots stored for 1 year at room temperature lose half of their beta carotene compared to the dried apricots stored frozen, which barely lose any beta carotene, and they still are a very bright orange color. So this shows very quickly that cold storage is definitely an important part of protecting some of these foods for this length of time. If we look at the resource needs for active refrigeration, though, for just 1,000 kilograms of food, we need 413 kilograms of extra resource system mass to keep that food cold. Now, we often get asked, isn't space cold? So can't we just store the food using space? Well, it depends on orbit and trajectory relative to the sun. So it doesn't necessarily mean that space is cold, depending on how your vehicle is positioned. So you would need thermal isolation from the habitat and a sunshade and some sort of atmosphere control. We still don't want to store our food under vacuum. And we haven't yet conducted a full engineering feasibility study to see if the resources for active refrigeration or passive refrigeration would be more optimal. So the risk and reliability of these two systems is not yet known. Now, I've already talked about the importance of variety and choice. And one of those things is a lot of the fruits and vegetables that we get here on Earth, we eat fresh. And we can't really do that in spaceflight, especially where we need very long shelf lives at room temperature. So one of the things we've been trying to do is provide more variety and choice in processed fruits and vegetables, and also other kinds of fish. So we do use commercial items where we can get them. A lot of the salmon and tuna that's available in the laminate lightweight packaging we do use, but that still limits the types of fish that you can provide. So we've been looking at providing other kinds of fish that provide a choice in other sorts of processes, such as freeze-dried. And one of the other things that becomes very important too is we do sensory evaluations in our lab using sensory panels, but that does not indicate in a closed system over a long time how crew will perceive an entire food system and how they will use that food system and how it will support their health and performance. So we do use analogs where crew are selected from a volunteer pool to be astronaut-like, and then they perform a ground-based mission. And there are 3 locations right now that are running analogs like this. And one of those is the Human Exploration and Research Analog at NASA in Houston, Texas, and the 20-foot atmospheric chamber at NASA JSC in Houston, Texas, and then also the Sirius NEK facility in Moscow, Russia. And we recently did complete a study where we were looking at how do we reduce the food system mass for the upcoming Orion missions. And so we used nutrient-dense meal replacement bars for 1 breakfast meal a day. And this was, we put them into 4 30-day missions with 4 astronaut-like individuals under isolation and confinement who were given operationally relevant tasks and put under operationally relevant stressors. We calculated their caloric provisioning, and we looked at the outputs. So in association with meal replacement, we did see reduced caloric intake, reduced weight, reduced meal satisfaction. And then we also looked at some responses from crew over this time as well. And we saw a reduced desire to eat, reduced energy, increased boredom, stress, and happiness, and symptoms of anxiety and depression. Now, this was over 30 days, and this was in comparison to regular breakfast meals. Now, we did not see physical or medical symptoms from these outputs. These were indications of directions. So over a 30-day mission, you probably could do something like this. But the interesting part is, even over a 30-day mission, we saw them eat less when they were given the meal replacement bars. And we saw them that they were less satisfied with the meal replacement bars. And crew comments indicate that this is because there is a restriction in variety. There's a restriction in choice when for a whole meal every day, which was about 750 calories, they didn't have choice. They didn't have variety. They basically were given a meal replacement bar. So this becomes very important as we look for strategies to reduce resources. And this also indicates the importance of why just providing a supplement doesn't really work, because everybody wants choice and they want variety in order to maintain interest in consumption and satisfaction from one of a very important part of choice during spaceflight, which is the meals. So there are other strategies we could look at, such as packaging design. Increasing fat content comes up because that is a way to increase calories per gram. However, we have to be very careful because we do not want to exceed our saturated fat limit, and increasing unsaturated or healthier fats can become a challenge because they're more unstable. So we do have saturated and unsaturated fat limits, so increasing some unsaturated fat slightly could be a way to increase density, but it is a great challenge to do that. Reducing water content, if we're recycling water, is another potential partial solution, but also crew like the choice of having some foods that are already hydrated. Providing a fully freeze-dried system is not necessarily an acceptable solution either. So we have to look at mass reduction strategies with acceptability and variety considerations to maintain crew consumption, health, and performance. So we can also look at bioregenerative foods. There's a lot of positives about starting to add these. They have psychological appeal, they add some nutrient density, fresher food, customization. And if we're going to become self-reliant and earth independent, we need to start moving in a direction where we're able to start generating our own foods in space using the resources that are there. This is a big challenge. There are a lot of considerations that still need to be solved, but we have started growing some crops using the veggie on the International Space Station. So Kennedy Space Station does a lot of this work, and they've grown some leafy greens in the system that the crew has very much enjoyed, as can be seen by all the pictures that they take, which does show the importance of having some of these systems, the importance of food, the importance of fresh foods, and the addition of variety, the addition of flavors and textures to their meals. But there are a lot of limitations still with these systems. So you have the risk of food scarcity. Even with the few times that they've grown foods, they've already had challenges with watering and microgravity. So there's a lot of considerations that they have to overcome. There's a microbiological risk that's added. How do you test these foods, make sure they're safe when you cannot do these tests on the ground? A foodborne illness in spaceflight will be much worse than it is on the ground because your medical capabilities are less. And also because you're in microgravity for a lot of the way. So we also have a higher crew time requirement when we're looking at some of these systems, and depending on what the crew is doing. So if they're doing a lot of science, if they're going to be exploring, they won't have time to put into their food systems. There's also a lot of infrastructure. So even if the food system going up weighs less, how much infrastructure is required? How much infrastructure is required for this system to integrate with the other systems, including the water system and the air system? What kind of volatiles is it producing? So there are a lot of considerations when you start looking at adding bioregenerative systems. It's similar to here on Earth. It's impacting every life support system when you start growing food and all the different waste streams it's producing. So what are all the inputs and what are all the outputs? So right now, bioregenerative foods are at a low technology readiness level, but we are hoping to start integrating salad crops So having some pick and eat salad crops just as a supplement to the prepackaged food system. And then we can start validating the technologies and the reliability and start increasing dependence on crops and potentially other strategies. So we did recently look at 3D printing of foods. There's the idea behind this would be some sort of automated processing. So there was a company in SMRC that got a Small Business Innovative Research grant to show the ability to print different kinds of foods. They printed a dough, a sauce, and a cheese as a proof of concept. And the idea here was that if you're on these longer duration missions and you want to add precise nutrients, if you have crew that are avoiding some of the foods because they don't really like those and they're missing certain nutrients, you can provide it in a customizable way. So this might not be a whole food system, but it would be like a supplemental part of the food system. And we still do not know what the future food systems for exploration actually will look like, but we do know that these food systems will have to be nutritious. They'll have to provide all the nutrition in an acceptable way with variety. They'll have to be safe, and if they have to be tested, all of those considerations will be included in their resources in the mass trades and the risk trades when deciding on food systems for long duration. And all of the resources for those food systems and their integration with other systems such as water and the air system will also have to be considered. Ultimately, whatever food systems use has to show that it can support health and performance for these crews as they're doing these demanding tasks. And one of the questions that I do like to ask is, the first missions will probably be exploration missions with a few crew members who will be doing other tasks all day. And if we think about our own lives and when we come home, we want to enjoy our meal. So what are we willing to do in our own kitchens at home? And exploration missions will focus more on what are we willing to do in our own kitchen. So if we're using novel technologies, which could be possible, how can we do this in a way that most people would want to do this in their own kitchens? Are there technological advances that we can include? Are there ways to reduce the mass and the resources? Are there ways to make the process fun and exciting that you'd want to do it every single day if you are using a new system? Or are some of these systems really for the future, for colonization, when we have people that are dedicated to food production, like we have people dedicated to food production here on Earth? So we do have a Space Food Challenge coming up. It's in development and we expect it to be open to registration in early 2021. We're going to be looking for novel solutions to these food challenges. We're looking for teams to compete to win prize money across multiple rounds of competition. And there's some websites attached to it that are shown here. So if you're interested in that, take a look. I want to bring this back to our key points that the food for spaceflight has to be safe. It has to provide all the nutrition within a closed system in an acceptable way where the crew can find the variety and the choice that they want to eat. And food must ultimately promote health and performance so that they can perform their highly cognitively demanding and physically demanding tasks. And ultimately, it also has to fit within the mission resource constraints, which are often very, very restricted for these missions. I want to mention that there are a lot of different groups that work on these challenges, and we do also have grants for these challenges as well. So I want to thank you for listening, and I will be happy to take any questions.